Okay, let's start the next talk. So it's my great pleasure to introduce the next speaker, Svjetlana Terzic from University of Montenegro. She's going to talk about modular spaces of relative pointed stable curves on Grassmannian GN2. Please start.
Thank you very much. Thank you for the invitation to give a talk. It's my pleasure. I'm going to speak about my recent joint result with Victor Buchstaber, which actually these results appeal on our long time investigation of the torus action on the manifolds and in particular on the Grassmann manifolds. And I'm going to explain you one connection that we established between the, a relatively recent notion of moduli spaces of weighted point stable curves and compact torus action on Grassmann manifolds, in particular Grassmannian GN2. Just in the short, to have an overview of what I'm going to speak about. Actually, as I said, we have recently been studied the equivariant topology of Grassmann manifold GN2. Grassmann manifold GN2, they are just complex Grassmann manifolds, which consists of two-dimensional complex subspaces in n-dimensional complex space. They are as well homogeneous spaces. And we studied the canonical action of the compact torus. Actually, we have the action of the compact torus on Cn, standard coordinate-wise action, and induces the action of the compact torus on a Grassmann manifold, two-dimensional complex subspaces. And maybe 2 years ago, in a paper published a year ago, I think, we constructed just by topological methods a model for the orbit space. What does it mean, a model? It means something that in some sense, it means that we have actually we constructed the model. It is some space UN, which is actually the product of the hypersimplex, standard hypersimplex, and some smooth compact manifold together with the continuous projection. And this is a model. Maybe I will say a few words later. This is the model. What do we mean by that? We mean that there are open dense subsets in UN, and in these orbits, such that this projection is diffeomorphism between them. This is diffeomorphism, and actually it preserves the combinatorial structure. We have here the combinatorial structure, which I'm going to explain, and here also some combinatorial structure. And actually we constructed this model, which actually in some topological sense very well approximates this orbit space. And then for this space Fn in our model, we prove that it is diffeomorphic to the well-known Deligne-Mumford compactification of the stable genus zero curves with Denmark points. And so somehow our ingredient, the space Fn, which appears in our model, is actually very well known and very well studied. We obtained it completely independently. We came to this space Fn from the point of view of topological description of our orbit space. And after that, we realized that we can prove that actually it is the Deligne-Mumford compactification of moduli spaces of n-pointed curve. A theory of stable curves of genus zero has recently, not recently, it was almost 20 years ago, enriched by Bernard Hassett, where he introduced the notion of for arbitrary genus G. I'm going to restrict myself to the genus zero. It is enriched by Hassett by considering the stable curves, weighted stable curves. What does it mean? To each point is assigned a weight, and such that it behaves nicely. And what for this space Fn, I said we established in our model, we established the relation with this well-known Deligne-Mumford compactification, and then what I'm going to present you today is that also it can be established relation between these Hasse spaces. So the spaces, the moduli spaces of stable curves with weights assigned, with assigned the weights, and actually the toric topology, equivariant topology of the Grassmann manifold. In some sense, I'm going to show you that we realize that the orbit space of the Grassmann manifold Gn2 by the action of the compact torus can serve as a universal object for all these moduli spaces. Now just to remind you to follow easier the things. So we consider moduli space MON. MON moduli space is just moduli space of compact complex algebraic curve of genus 0, so CP1. And by moduli space, we consider all such with MON complex algebraic curves of genus 0 with n marked distinct points. It can be considered as a space, as a configuration space of n points on CP1 and different points on CP1 up to the action of the projective group. Say for n equals 3, this moduli space, so when we consider this moduli space we consider CP1 with 3 marked distinct points, but then we have always homography which maps then to these 3 points, 0, 1, infinity. So this space MO3 is just a point. In a case n equal 4, we consider CP1 with 4 points, and then if we apply some Möbius transformation, then it is isomorphic to CP1 0, 1, infinity with one parameter t, where t is not 0 and infinity, since these points are assumed to be different. So the space MO4 is just CP1 minus 3 points, and so on. So in general, CP1 with this space MON with n mark points is given this way. It's actually a subset in CP1 n minus 3. This space is not compact, as well as n is bigger equals 3. And now it's a well-known problem of compactification. It's solved well-known problem of compactification of these spaces. And of course, one can compactify some space in many different ways, but it's a problem. One can just what one point compactification, we all know, but the problem is to find a good compactification. So it should be itself a moduli space, which parameterize in a natural way generalization of the object from MON. And it is well known in this context, it is well known the Lin-Mumford, which is equivalent to Grothendieck-Kunkel compactification by stable curves. I'm not going to explain. There are many definitions of stable curves. Stable curves. These are the curves that have may say singularities of a type node. All mark points are different, and one can say that the only isomorphism of CP1 that preserves the fixed points is actually identity. Or there are the combinatorial equivalent definitions, but the stability condition of these curves. These are curves with n of genus 0 with n mark fixed points, which satisfies additional condition, stability condition, and stability condition can be formulated many ways. One of the way is that this divisor is an ample divisor for the canonical class of the curve C. And then, so the compactification of MO4, if you remember, MO4 is a CP1 minus 3 points. It will be CP1. MO5 will be, say, known the Peso surface of degree 5. Yes.
So this is my lack of understanding. I guess you are adding the stability condition, right?
Yes.
And to me, that would have intuitively mean that you get fewer points than before, that you're making your thing smaller because you have another condition. Something that was in there before is not in there now because it might.
Yeah, no. This is compactification.
Yeah, that's what I don't understand. Why is it? Why is it not getting smaller?
It's not get. I mean, the stability in condition is no, because stability in condition now you consider the curves which can have singular points, and the singular points may have only be the nodes, the double singular points. Okay. Okay. And then what are this is ordinary stability condition when we have ordinary points without any weights. What the paper Bernard Hassett actually, which was somehow revolutionary paper in this direction. They are after that many more papers studying this notion. Is he assigned, roughly speaking, we have the same situation, but we have also the stable curves, but now we want to assign to each stable curve weight. And one has to take into account that any curve has a weight. And then he formulated a stability condition in this way. So he said, so we have a curve of genus 0. We have a mark points. In this case, the points are not required to be different. They may coincide. And this is said to be A-weighted. A-weight is stable if it is given a function of which to each point assigned a weight. A weight is some number between 0 and 1. And this divisor is required to be ample. So each point is multiplied by its weight. And if some points collide, then the sum of weights is required to be less equal to 1. And this is stability condition given by Hassett. And he considered moduli spaces of such curves. And from this stability condition, by degrees, it follows that the sum of the weights has to be bigger than 2. Then if we take that all weights are equal to 1, this M bar or Hassett space is just the Riemann-Mumford compactification. And just in the language, it's far from me, but the language of algebraic geometry, Hassett proved that actually exactly what the Riemann-Mumford proved, that MOA is a smooth connected Riemann-Mumford stack proper over Z. Okay, then what is nice? Then in this paper, he proved that among these spaces, weighted spaces of stable curves, one has reduction and forgetting morphism. So if we have two weighted spaces, stable curves, weighted stable curves, moduli spaces, then if all weights from here, BI, are less equal than AI, then there is birational reduction morphism. So it's a rational map. It has inverse rational map. And in addition, he proved that if we have some set of weights and say we forget some weights from here, but such that the weights which are left satisfy this stability condition, then we have a forgetting morphism. This is just a morphism. This is not, there are no birationality. And I shortly write down here how these reduction and forgetting morphism works. He just consider one takes a curve and consider these components, consider these points of the curve along these divisor fails to be ample, and then it contracts it to the points in order to get correct map. And then now what is interesting, so when we consider these Hassett construction, and since these spaces of weighted stable moduli spaces of weighted stable genus 0 curves, it appears these weights. We have the weights, and as I said, these weights are, I put here Rn, it's the same Qn. In these weights, as I said, the weights are some numbers here such that the sum is bigger or equal to. And then one can define this is we are in Rn, and it is defined in his paper chamber decomposition, coarse chamber decomposition, and fine chamber decomposition of this domain of admissible weights. I mean, it's nothing. If one reads a little bit from algebraic geometry, especially, I think, great paper by Michael Tadeus from Journal of Mathematical Society from 96, 97, actually on the abstract level of algebraic geometry, it is written there, but here it's rewritten in a very concrete terms. We have considered this domain of admissible domain of weight data, and then one can consider this hyperplane arrangement. I just here coarse chamber deposition consider, and this hyperplane arrangement gives a chamber decomposition of Rn, and intersected with this domain of admissible weights, it gives the chamber decomposition of this domain. So one can consider the chamber decomposition of this domain by this hyperplane arrangement. And then it is defined the boundary. This is not a topological boundary, but this is the boundary is defined to be the set of all such weights where this sum is 2. And one can, it's not easily to realize that this boundary is actually the interior of the hypersimplex delta n2. And what, okay, is interior hypersimple delta n2. And what I did not write, here maybe it will appear later, but I want to emphasize, what was the result also has proved. When we consider the chamber decomposition of this weight of this domain of weight data by this so-called coarse hyperplane arrangement, then the weighted space m bar OA is a constant on each chamber, does not depend on A. So say we take some d omega is a chamber from d on given by this decomposition by this hyperplane arrangement, and we take A from this d omega, we consider m bar OA weighted space, it does not depend on A. So it's isomorphic. So in other words, these weighted spaces, moduli spaces of stable genus zero curves, weighted spaces are constant on each chamber of this chamber decomposition. It is proved in his paper. And okay, then what is further interesting? He established the relation between, I just shortly remind, the relation between these moduli spaces and the geometric invariant theory quotient. Actually, one can say, if we consider CP1n with diagonal action of the projective group, and then one can consider such a so-called fractional linearization of this action. I mean, I do not have time to talk about that. As I said, one can find all these things in more general setting in this paper of Tadeus in Journal of Mathematical Society, that when we consider, say, Li is a canonical bundle on ith factor, and then we consider some tuple of rational numbers, and then consider this tensor product, this element actually is a fractional linearization. It's a member, it's element of so-called Néron-Severi groups, which is contained in Picard groups of general linearized line bundle. And then when we consider this tensor product, it's a line bundle, and it defines so-called fractional linearization of these actions. And if we assume that the sum is equal to 2, then just in order to construct geometric invariant theory quotient, one has to consider semi-stable and stable points, and the semi-stability condition of a point can be summarized as follows. So, I mean, this line bundle is typical when all stable points are stable and atypical otherwise. And this is all preparatory notions, so one can define the geometric invariant theory quotient. So we consider CP1N quotient, geometric invariant theory quotient of CP1N by this action defined by linearization O, and this linearization O is defined by some T1 Tn from Qn. And what has it proved? He proved that if we have a typical linearization, so none of the coordinates for L is delta O, none of the sum of the coordinates is 1, then so we consider some element from the boundary of delta On. So it's some tuple of n rational numbers, none is 0, everyone is less equal 1, and sum is 2. And we consider linearization of the action of projective algebra of PGL on a CP1N defined by this linearization. Then there exists neighborhood of this point L such that the intersection U with the domain of admissible weights of U is an open chamber in delta On, is an open chamber in domain of admissible weights. And for each A from that open chamber, the moduli space is isomorphic to the geometric invariant theory quotient of this action. If the linearization is atypical, so some of the points are allowed, some points are allowed to be 1, there this is not an isomorphism, but there exists natural birational morphism. So he established connection between his moduli spaces of stable weighted genus 0 curves and the geometric invariant theory quotient of the CP1N defined by the action of PGL2, diagonal action. And then I want to mention here, because among these spaces, because there are a lot of studied in physics and in a connection with the different problems, they are so-called Grassmannian spaces. Grassmannian spaces are spaces, they are moduli spaces of stable curves of genus 0, whose points are painted by black and white. And at least it has at least 2 pointed painted by black and 2 points painted by white, and all white points are pairwise distinct and distinct from black ones, while black points are without restriction. The people who work with quantization and other quantum homology, cohomology operators and other things, they often meet with the Grassmannian spaces. And it's a result. Mannion proved that actually this Grassmannian space, after Hassett published his result, can be realized, it's isomorphic, can be realized as a moduli space of weighted curves. And we proved actually that this, that somehow this weight vector A, Mannion proved actually that this weight vector, where we have a K, that Mannion proved where AK plus 1 AN he chose to specify it, and we proved that actually that Grassmannian space does not depend on these weight vectors of these AK plus K plus 1 KN AN. Okay, these are, I mean, These things I presented now, up to now are just an overview of somehow known things. And now I would like to relate this with our work on a Grassmann manifolds. As I said, so this was one part about some known results from algebraic geometry, and now this is our work. We studied, as I said, T and action of GN2, compact torus action of complex Grassmann manifolds, two-dimensional complex subspaces in a CN, and this action, just to remind, extend to canonical action of the algebraic torus. And then we have the standard moment map. I'm not there. I'm just going to recall the standard moment map defined by the Plucker coordinates. We have a Plucker coordinates, and lambda I are the vectors from Zn. I are two-dimensional subsets from 1 to n. Lambda I are the vectors which have a 2 places 1 and the other n minus 2 places 0. Just to have the image of this moment map is a hypersimplex delta n2. Now, using this Plucker embedding, one can define the stratification of Grassmann manifold. The strata for each subset sigma of 2-element sets from 1 to n. One can define W sigma. It's consisting of all points from Grassmann GN2, such that the non-zero Plucker coordinates are determined by the subset sigma. Such element W sigma, if it is non-empty, we call the stratum, and the sigma for which this W sigma is not empty, we call the admissible set. Then GN2 is the union of all these W sigma. All W sigma are C star and invariant. So we have and W sigma do not intersect. We have a certification of Grassmann manifolds by the Plucker coordinates. And we proved, when we were doing this, that when we apply the moment map to W sigma, we will get that the image of the moment map is interior of the interior of the polytope A sigma, where polytope A sigma is a convex half of those lambda I where I are indexed by sigma. We call P sigma an invisible polytope. And what we further prove that, as I said, W sigma is invariant under the action of algebraic torus. And so the quotient by the action of algebraic torus is an algebraic variety. And we proved actually that this fibration is trivial. So we have a homeomorphism between the orbit space of any strata on any stratum by the action of the compact torus and this product. Mm-hmm. Admissible set is a set sigma which is subset here for which this W sigma is non-empty, because it may happen that from some sigma it will be empty, for some it will be non-empty, and just to sort them down we call them admissible. And then we have here the main stratum. The main stratum are given by all points in the Grassmann manifold for which all Plucker coordinates are non-zero. So it is an open dense set in a Grassmann manifold. And as I said, since we have that it is this orbit space, from the previous slide, we actually proved that the orbit space of each stratum is homeomorphic to this. So the orbit space of main stratum, since admissible polytope is going to be the interior of the whole hypersimplex, times Fn, and it is open dense set in the orbit space of the Grassmann. Fn is just the orbit space by algebraic torus, and it can be written explicitly in this way. It is just the intersection of some cubic hypersurfaces in CP1 on degree n. Actually, it is not difficult to see, because we can here work in a chart. Actually, we can fix one chart. What is one chart? We can fix Plucker coordinate, which is non-zero, write down the main stratum belongs to any chart, write down the main stratum in the terms of local coordinates, then act by the algebraic torus and see what is the quotient. And now this here is an open dense set in this orbit space. So it means that there is compactification of this product, which will give us this orbit space. I mean, it's difficult to write down explicitly this compactification, but what we did, we constructed the compactification. This is of this factor here, which is the compactification of this factor here. It means the compactification of this orbit space, which is going to be the model for our orbit space. So what does it mean? We constructed the compactification of this factor such that we will have a projection from this compactification to our orbit space, which is going to be diffeomorphism on a smooth open dense submanifold, on the open dense submanifolds. How we constructed this? How we constructed the model, this compactification? Well, you will see somehow then how we establish the relation with Hassett construction moduli spaces. That's the reason I'm presenting this construction. We have, as I said, we have the family of admissible polytopes. The family of admissible polytopes are polytopes which we can get as images of the strata by the moment map. And these admissible polytopes, they sit inside the hypersimplex delta n2. They may intersect. I mean, they behave arbitrarily. We don't know. The situation is much more complicated in a case of toric, quasi-toric manifolds. We do not have. In that case, the admissible polytopes are the whole simplex, and it faces. Here, the situation is much more complicated. So we can intersect these. We can intersect these admissible polytopes and obtain the chamber decomposition of the hypersimplex. So all possible intersection of admissible polytopes. So we consider all chamber decomposition by all possible intersection of admissible polytopes. Then we consider the induced moment map. Moment map is invariant under the action of Tn, so we have the induced moment map. Then we consider the pre-image by the induced moment path of a chamber, C omega hat. So if C omega is a chamber, C omega hat is a pre-image. And then we proved that they also behave nicely, that C omega hat is homeomorphic to C omega times F omega, where F omega is actually disjoint union of all spaces of parameters F sigma. F sigma are the orbit spaces of the strata by the action of algebraic torus, which such that sigma belongs to omega. The space of parameters of main stratum is contained in F omega, and F omega is a compact space. Actually, what one can deduce from the results of they were studying these spaces by Glenfarne, Serganova, Goreski, McPherson. They have one even joint paper, and actually, it's not written explicitly there, but one can somehow figure out it from that. That when we consider the chambers for this chamber decomposition, then and consider the pre-image of a point from a chamber in this orbit space, that pre-image up to homeomorphism does not depend on a chosen point from the chamber. So when we go through the chamber and consider pre-images of a point, these pre-images topologically do not depend on a chosen point from the chamber. So what do we get? We get that the orbit space is actually the union of this C omega hat, and this is the union of these products. And now, as I said, we wanted to compactify this. We wanted to compactify this product in order to obtain the model from this orbit space. The problem is the compactified delta N2 interior. It's I mean, obviously it has to be delta n2, but these Fn, I mean, ordinary F, which is the space of parameters of the main stratum, was not easy how to compactify in order to get a model. And we introduced the notion universal space of parameters. That will be compactification of the space of parameters Fn, which will behave nicely under all our constructions. So that we will have a projection. Then here we have the certification. The pre-image of any strata is going to be appropriate product here. Here will be admissible polytope, and here some space an Fn, which we call the virtual space of parameters. And there is this projection from this F sigma tilde, since this part, if you remember, is a product space sigma 0 times F sigma. So this F sigma tilde is larger than F sigma. So we require that there exists such a projection such that when we go by Gn to this orbit space and by this homeomorphism to this, that it coincides with this projection from here to here. And how we constructed these spaces Fn, which I explain now. First, as I said, our Fn is given an intersection of these cubic surfaces in CP1n, where each of the parameters Cij prime is not allowed to be 0, 1, infinity. And the first compactification is just a closure Fn in CP1n. So to allow this point to be 1, 0, infinity. But this compactification does not work for us well. So it doesn't satisfy this condition I mentioned. So we found out that there is nice construction due to many authors, De Concini Processi, Fulton McPherson, and Lee, called the wonderful compactification. Wonderful compactification, it may compactify already compact objects in order to resolve some singularity that appears in some context. There is a notion, I mean, one can find it, a smooth, wonderful compactification of a smooth algebraic variety generating by building set of a smooth subvarieties. And we proved actually that in this Fn bar, there exists a building set such that a smooth compact manifold obtained as a wonderful compactification by this building set will be the universal space of parameters for Gn2. Actually, we starting from this closure of Fn bar in CP1n, we applied the wonderful compactification, obtained the smooth compact manifold, which is going to satisfy our condition. And now here it appears so-called virtual, as I said, in virtual spaces of parameters. Virtual spaces of parameters gives all universal space of parameters. For the main stratum, they are Fn tilde, and we have this projection. And what is interesting, when we are inside one chamber and consider the union of virtual spaces of parameters where sigma belongs to omega, which determines the chamber, this union is disjoint, and so this union is joint, so one can define the projection from Fn to F omega. F omega is union of all F sigma, where sigma is of omega, in this way. P omega of y, we just take y from here. There exists unique F sigma tilde, which contains y. We have projection from F sigma tilde to F sigma. On that way, we define this projection. And now we can construct the model, just in a short. So the model is delta n2 times Fn, where this orbit space is the union of pre-images of the chamber. And how is defined the projection? We take x and y. When y is from Fn, x belongs to some chamber C omega. From this y, we have the projection from Fn to F omega. So x p omega y will belong to C omega times F omega. We apply homeomorphism F H omega and go to C omega hat. And this is for the chambers which belong to interior. For the chambers which are on the boundary of delta n2, we notice that the boundary of delta n2 consists of hypersimplices of smaller dimension and simplices. So the pre-image is going to be the union of the orbit spaces of Grassmannian of smaller dimension and orbit spaces of complex projective spaces. Here the space of parameters is a point, universal space of parameters. Here the space of parameters of the universal space of parameters is Fn minus 1. And we actually proved that the space of parameters of the Grassmannian on the boundary actually we get as a result of by forgetting one coordinates from Fn. So to summarize, what are the structural data of our model? It's a universal space of parameters, which we constructed by the wonderful compactification, virtual spaces of parameters, spaces of parameters of chambers and over the chambers and strata, and the projection from the virtual to ordinary space of parameters from Fn to F omega, and this is forgetting one coordinate. And what we proved that this model can be completely realized in terms of moduli space of weighted curves and morphism between them. The first what we proved is that the space of parameters of a stratum. We have a stratum. We have the orbit space by the action of the algebraic torus. It's actually a lot of things can be done in terms of isomorphisms and so on. I'm speaking in terms of topology and homeomorphism. So the space of parameters of any stratum is homeomorphic to moduli space, ordinary moduli space. Then we proved, as I said in introduction, that universal space of parameters is diffeomorphic to the Deligne-Mumford compactification. Further, then we use the result of David Mumford and Francis Kirwan on categorical quotients and Kirwan of geometric invariant theory quotients, and prove that space of parameters of the chambers. So we have a pre-image of the chamber. It's C star n invariant, and we consider the action of the algebraic torus. Spaces of parameters of the chambers are actually homeomorphic. We can even say isomorphic to the geometric invariant theory quotient defined by the ample line bundle, defined by this linearization. Linearization is given by the point from a chamber. It does not the point of the chamber. Combining the results of Hassett, which established the connection between the geometric invariant theory quotients and moduli spaces, we actually prove that if you have a chamber of maximal dimension, then the space of parameters of the chamber is actually homeomorphic to this moduli space. If you have a chamber of dimension less than n-1, we have a birational morphism. Then here we established how these virtual spaces of parameters that we described, how they are all homeomorphic to these. We described the virtual spaces of parameters. Actually, these are these universal space of parameters, and they are all modular spaces. And so, I just would like to mention that when we consider the family of these chambers in delta n2, and we consider the family of chambers in Hassett decomposition, that from this proposition, from this corollary, for each chamber there exists F omega. We have an ejective map such that to each chamber C omega, it assigns chamber D omega such that D omega belongs to D omega bar, and actually the space of parameters F omega for this chamber is homeomorphic to the moduli space which correspond to this chamber D omega. Then what we further proved? We further proved that our projection map, which we have in our model, it coincides with the forgetting map by Hassett. And we proved that the projection from the universal space of parameters to a chamber, when dimension is n-1, and the reduction corresponding, since Fn is this moduli space, F omega is this moduli space, it coincides with the reduction morphism of Hassett. As far, may I have some few minutes? As far as the Grassmannian spaces are concerned, the Grassmannian spaces are, as I said, they are also realized as these moduli spaces of weighted curves. The chamber which belong to which belong this vector A does not satisfy this condition. It's not in the image of this moment map, but nevertheless we can prove that there exists a chamber such that we have a birational morphism from the Grassmannian space to this chamber. And actually one can prove it for all chambers, maximal dimension satisfying this condition, and all chambers of dimension n-1 less equal n-1. As a result, there are plenty of consequences. Since our Fn is a blow up, is a actually wonderful complication Fn bar. It's iterated blow ups of Fn bar. We have the blow down morphism, and we also have the birational reduction birational morphism, since here all weights are 1 and here are less equal 1. And we prove the divisor for this morphism coincides. So we prove that the Grassmannian space is isomorphic to this space Fn bar, which is compactification, which is in CP1n. Okay, then I will skip this for demonstration for n equal 5. And just to mention, because here a lot of about toric varieties, but to mention one thing, why I mentioned Grassmannian space, because combining the result of Manin, Caprano, Gelfand, Serganova, one can see that Grassmannian space with n painted white points is a smooth projective variety over permutahedron variety, and it actually can be obtained as a closure of on principal orbit in a complete complex Wag manifold. So according our results, these permutahedron variety can be mapped up to birational morphism to the orbit space of the Grassmannian GN2. And now one can ask the question, okay, since this permutahedra variety is a graph associahedra variety, so which these varieties can be related to our orbit space through the moduli spaces of weighted curves, and there are not many. There are not many overlapping, because there is the result which says that toric variety, which is variety associated with graph G, is isomorphic to a moduli space of stable genus zero curves to weighted moduli space if and only if G is iterated cone over some discrete set of vertices. So as a corollary, we can see that the graph associated toric varieties for the graph G, which is cone, which is actually iterated cone over some vertices, can be mapped by birational morphism to this variety. And as I mentioned, in this way we prove that our orbit space is a universal object for all Hassett spaces. First, all Hassett spaces are birationally equivalent. One can easily see that. There are no morphism between them in general. Between Grassmannian spaces, there exists birational morphism. But what we prove that using this, that all our spaces of parameters of chamber are birationally equivalent. There are no birational morphism between them. But what is somehow final result is that any Hassett space, moduli space, there exists birational morphism to some space of parameters F omega of our orbit space GN2 by Tn. So up to birational morphism, any Hassett space can be mapped to a variety in a orbit space GN2 by Tn. And what would be related to this? There are many questions that can be asked here. First, one can consider geometric complexity of torus action. when we have the torus acting of manifold M2n with the moment map and reduced moment map, then when k is equal n, pre-image of a point is a point. So we have a toric, quasi-toric, toric manifold. When k is equal n minus 1, in most cases, when we take 2 points x and y from the interior of the moment polytope, then the pre-images are homeomorphic. So we take loose moment map from the orbit space, we take the pre-images are homeomorphic. So when we consider, say, G42, we proved it in our paper with Victor Matveich, that pre-images are homeomorphic is CP1. When we consider T3 action, flag manifolds are mentioned several times, the pre-image is also going to be CP1. Then the pre-image of the Hamiltonian T and n minus action on a symplectic manifold, the pre-image of the points from the interior are also all homeomorphic. Where k is less equal n minus 1, then we may have we have an example that the pre-images are not homeomorphic. For the first example, which appear is n equal 5. We take Grassmann manifold Gn2, moment map from Gn2, G52 to T5 to delta 5,2, and then we may find 2 points such that the pre-images are not homeomorphic. And so the orbit space is much more complicated. And so what are the problems? Classify, at least not classify some torus action. One can classify the pre-images for some torus action of the points from up to homeomorphism, birational equivalence. In our case, in a Grassmann manifold Gn2, since the pre-image of a point is actually the space of parameters f omega for the chamber that point belongs, an appropriate problem would be find criterion for classification of these spaces in terms of Hassett and the Svjetlana spaces. And I just want one more thing to mention. Since our f omega, we have when we have the complexity of the action in also algebraic geometry, when we have the action of algebraic torus. In our case, our space of parameters f omega are nothing else but the orbit spaces of the union of the strata for sigma is omega by the action of algebraic torus. So we related our spaces of parameters f omega with the moduli spaces, but our spaces of parameters f omega belong to the problems of our space of parameters f omega are actually the orbit spaces by the action of algebraic torus. So somehow these results in the research is related to the action, to the torus, algebraic torus action of the positive complexity. Thank you very much. I'm sorry for.
Thank you.